Hi everyone! In this video we're going to be talking about the superposition principle, and we're going to look at the method of undetermined coefficients once more. Okay, so our superposition principle says the following. If y1 is a solution to our second order differential equation and y2 is a solution to this second order differential equation, notice what they equal. It's different terms over here. We call this one f1, this one f2. Then for any constants k1 and k2, then the functions, those constants times these solutions, so k1 y1 plus k2 y2, the sum of those two is a solution to our differential equation if it equals a combination of those two terms, those two non-homogeneous terms. Okay, so it's sort of just combining things that we've kind of done already previously with our method of undetermined coefficients. And so we'll break this down and you'll see it through examples. Okay, so let me first remind you, we went over the method of undetermined coefficients. So if you haven't already checked that one out, please watch the video about that and we go through this process. But basically it comes down to what the non-homogeneous term looks like depending on what type of solution we're going to work with. So if it has this form, then our solution has this form, and we pick S depending on the roots of our auxiliary equation. And if our differential equation equals these types of terms, these non-homogeneous terms, then our solution has this format down here. And again, we pick S depending on the roots of our auxiliary equation. Okay, so let's try this one out. So find a particular solution to y double prime plus 3y prime plus 2y equals negative 9t plus 20e to the 3t. Notice that we have two terms over here. We have two non-homogeneous terms that our second order differential equation equals. So this is exactly what we were talking about and why we're going to use our superposition principle here. So let's start with the auxiliary equation that's associated with our homogeneous equation. If we pretend that this equals 0, and so we have r squared plus 3r plus 2, and we find the roots. We get that one of them is negative 2, and the other one is negative 1. Okay, so now what we're going to do is we're going to break this apart and consider each of these non-homogeneous terms one at a time. So we're going to say consider this second order differential equation that just equals the term negative 9t. Okay, so the format of that term is from cases 1, 2, and 3 of our method of undetermined coefficients. It has this format where we have c times t to the m times e to the rt. So if we just sort of match things up, c is negative 9, m is 1 because it's t to the invisible 1 power here, and then there's no e to the rt, so that means r must be 0. And now you compare your root r from this non-homogeneous term to your r values, your roots from your auxiliary equation up here, and then you determine which case you have based on that. So because r equals 0, and neither one of the roots of our auxiliary equation was 0, that's why we picked case 1. Okay, so we went over this before, but that's why it's case 1 out of the 3 first cases. And so we pick this solution format for our answer, and then case 1 says that S is 0. So now it's just a matter of plugging things in. So our solution y1 equals t to the 0, because S is 0. Because m is 1, we have these two terms, a1t plus a0, and then r is 0, so we have e to the 0t. Making it look a little nicer, y1 equals a1t plus a0. Okay, so now let's go a little further and find out what a1 and a0 equal. Okay, we can actually figure these out. So from our solution that we just found, if we differentiate that, take the derivative of y1, we're going to get, with respect to t, we're going to get a1. And then differentiate again, second derivative, we get 0. And then we can plug those values in to our differential equation. So where there's a y double prime, we're going to put 0. Where there's a y prime, we're going to put a1, and then where there's a y, we're going to put our solution that we came up with, a1t plus a0. and we know that that equals -9. And then how we're going to find A1 and A0 is just do a little rearranging. So notice what we have here. If we just sort of rearrange and group, let's start with the right side. On the right side, we have a coefficient on t, and then nothing else, so we could say +0. On the left side, we have t here, the coefficient is 2a1. Okay, so I grouped it here. 2a1 times t is going to match up with -9t. And then all the other terms, 3a1 plus 2a0, those have to equal 0 because there's no other term over here. And so this actually gives us a system of two equations. The 2a1 equals -9 because they're both the coefficients on t. And then 3a1 plus 2a0 has to equal 0 because there's no other term over here. And then use substitution after you solve for a1, and you'll get that a1 is -9/2 and a0 is 27/4. And so your final solution for y1 is -9/2 t plus 27/4. Okay, so we're going to pretty much repeat the process, but we're looking at the other non-homogeneous term from our original equation. So we're now just focusing on the 20e to the 3t. Our auxiliary equation is the same, so the roots are the same. And now we just look at the format of our non-homogeneous term. It has the same format as the last one. It's the c times t to the m times e to the rt. This time c is 20, m is 0, and r is 3 this time. Okay? And so remember what happens here. You compare your r value here, your root, from your non-homogeneity to the roots of your auxiliary equation, because 3 is not the same as -2 or -1. That's case 1 again. Okay, so this is the format of our solution, and s is 0 once more. Okay, and so we just plug in our values. S is 0, m was 0, r was 3, and y2 equals b0 e to the 3t. I just changed the variable to b because we're going to combine our two equations, y1 and y2, and technically the coefficients, if I stuck to a, they're not the same a's, so I just chose b to distinguish a difference. Okay, so let's see if we can find b0, and from our y2 solution here, we have the derivative of that is 3b0 e to the 3t. The second derivative would become 9b0 e to the 3t. And then substituting that in to this version of our differential equation that equaled 20e to the 3t, plugging in for y double prime, y prime, and y, and knowing that it equals 20e to the 3t, combine like terms, and notice what we get. On the left side, we're going to get 20b0 times e to the 3t, and on the right side is the same, and so that means b0, this one's easy to solve, b0 is just 1. Okay, so then our solution is just y2 equals e to the 3t. And so now our final answer, to answer the original question, by the superposition principle, our differential equation that had two non-homogeneous terms over here that it equaled, so it had a sum of two terms here, has a solution of our two answers, y1 plus y2. And so putting those together, we have our final solution is y equals -9/2 t plus 27/4 plus e to the 3t. And if you weren't sure, you can always check by differentiating this twice and then plugging in back to the original, y double prime here, y prime here, and then our answer y right here, and seeing if you get what we have on the right side. All right, so now the general solution, if y sub p, this is a particular solution, is a solution to our differential equation that equals some non-homogeneous term, and then c1y1 plus c2y2 is a solution to our homogeneous equation. So reminder here, we've worked with this in the past. This is our homogeneous linear equation. It equals 0. So if we have two things, the solution to our non-homogeneous equation here, that's y sub p, and then the solution here to our homogeneous equation, then we can actually put those together. We can say y equals the particular solution, y sub p, plus our solution to our homogeneous equation. We can combine those and call that a general solution to our non-homogeneous equation. Okay, so we're going to use this format of the particular solution plus our solution to our homogeneous equation, and that's going to be considered our general solution. So let's work that out here. So given that our particular solution, so y sub p, is t squared, so it's a particular solution to this linear equation, y double prime minus y equals 2 minus t squared, find a general solution. And then also find a solution given some initial values. Okay, so to find this particular solution, you would do what we just did, the process from the previous example. So this one I'm just jumping to the general solution answer because I'm telling you already this is a particular solution. But if you wanted to get this, you would do the process we just worked through. Okay, so we're going to start with finding a general solution, and then after, we're going to use the initial conditions to solve for some constants. Okay, so we're going to consider the homogeneous equation. So notice it's our second order differential equation, but we set it equal to 0. So then let me remind you, so this is something we've also seen previously. If we have our homogeneous linear equation, our solutions are of the form e to the RT. But in general, if we have more than one root to our auxiliary equation, hopefully this is sounding familiar. This is all something we've talked about before. But then if we have multiple roots, so R1 and R2, then we actually do a linear combination of those two, and we call that our general solution. Okay, and so let me remind you of the breakdown. Depending on the roots, if R1 and R2 are different, then your general solution is just a C value times e to one of your r's times t, plus a C value times e to the other r to the t. But the interesting one is when you have one repeated root. So let's say you have your auxiliary equation and you get the answer r equals something, and you get that twice, then your general solution is changed a little bit. Notice you have an extra t here. So recall when you have a repeated root, one of your terms of your solution has an extra t. So C1 e to the RT plus C2 t e to the RT. Okay, so those are things we've talked about previously. All right, so back to what we were working on. Our auxiliary equation for this homogeneous equation is r squared minus 1. Factor that, you're going to get r minus 1 times r plus 1. And so your roots are 1 and negative 1. Okay, so our general solution to our homogeneous equation, we just looked at that, we just remembered. It's going to look like C1 e to the R1t plus C2 e to the R2t. Filling in R1 is 1 and R2 is negative 1. We have this general solution. But that's to our homogeneous equation. Okay, so we're going to go a little further. And so the general solution to this non-homogeneous equation, this is what we just talked about. We said that a general solution would be y equals the particular solution plus the solution to the homogeneous equation. Okay, so we were given, in this example, the particular solution. We just found the homogeneous equation solution, so just put those two together. So our solution is y equals t squared, the particular solution, plus C1 e to the t plus C2 e to the negative t. All right, now that was the general solution. We're going to go ahead and also work and find C1 and C2 because we were given initial conditions. So from the first initial condition, if we plug in 0 into our solution, it should equal 1. So doing that and simplifying, we get an equation, C1 plus C2 must equal 1. Now our second initial condition involves y prime. So first, let's differentiate y. So our solution y right here, just take the first derivative of it. You're going to get 2t plus c1 e to the t minus c2 e to the negative t. Then use your second initial condition, plug in 0 into the first derivative, and we know that it equals 0. And then after simplifying, we get c1 minus c2 equals 0. And then you have a system of two equations. You can use substitution or elimination here, and you'll find out that c1 and c2 both equal 1/2. So then, put that all together, and our final solution here would be y equals our particular solution, t squared, plus, we found our coefficients, so 1/2 e to the t plus 1/2 e to the negative t. All right, so now let's revisit our method of undetermined coefficients and just modify it slightly. Okay, so the only thing I've changed here is what's in bold. So our method of undetermined coefficients is the same, except what we can say about this non-homogeneous term is that it involves a polynomial that's of t. T is your variable, and then with this format, we're saying m is the degree. Okay, so we're just sort of modifying how this looks a little bit. Instead of saying c t to the m, we're calling that a polynomial where t is the variable. Very similar down here. So notice the format of what this equals. We have same thing, p sub m of t is a polynomial of degree m, and then q sub n of t is a polynomial of degree n. All right, so just changing what it looks like as far as the non-homogeneous terms, just modifying the format slightly, but the method is still the same. And then a quick note on the second case down here. When you're working with this one here where you have a polynomial of degree m and possibly another polynomial of degree n, then what you're going to do is just pick the larger of m and n when you're trying to find a particular solution. So whatever number is bigger, you use that one. Okay, so let's try one more example. We're going to find a particular solution. Notice this is a third order differential equation, and it has three non-homogeneous terms that it equals. So what we have to do is we have to actually break it down into three different processes. Same process really, but three different equations. Okay, let's start with our auxiliary equation. Pretend this is a homogeneous equation, set this equal to 0, and you have r cubed plus 2r squared plus r equals 0. And then if you factor, you're going to get that one of your roots is 0, and the other one is -1, but it's repeated. Okay, so you want to make sure you remember it's repeated because that helps you choose which case you have out of your 5 cases. Okay, so we have to consider each non-homogeneous term, and we have 3 of them up here. So the first one, we're going to say, let our equation equal 5e to the negative t sine t. So we just look at the format of that term, and it has the format q of some polynomial, q sub n of t times e to the alpha t times sine beta t. Okay, so from our summary of our method of undetermined coefficients, the new slightly modified version, this format matches this format. Okay, so then we identify some things. What's in the front here, this 5, that's actually our polynomial of t. Okay, so that's q sub n of t. It's just 5, and so because we don't actually see any t's here, it's technically t to the 0. So we're going to say n is 0. Okay, so it's a polynomial of degree 0. And then right here, alpha is -1, and then right here, invisible 1, beta is 1. All right, so our roots associated with this type of non-homogeneous term are complex from our method of undetermined coefficients. That means we're working in cases 4 and 5. And so the roots are of the form alpha plus I beta. So if we fill in our values, that's alpha, and technically you could say plus and minus I. And those roots, that R value here, does not match what we got from our auxiliary equation. It doesn't equal 0. It doesn't equal -1. And so because it doesn't match, that's why we are going to pick case 4. And so for case 4, this is the form of our solution, this big old long thing, but we just fill in our values. and then S is 0 for case 4. So real quick, technically M is 0 as well, because there's no other term here with a cosine in it. So M is 0. So right here we say S is 0, M is 0. We figured out alpha was -1, beta was 1, and we do that for the second term as well. And then we simplify a little bit, and we get y1 is a0 e to the negative t cosine t plus b0 e to the negative t sine t. Okay, now we're going to repeat this process, but for our next non-homogeneous term. So we already worked with our 5 e to the negative t sine t. Now we're going to work with 3. So we're going to say our differential equation equals 3. Our non-homogeneity of 3 has this format, p sub m of t times e to the rt. And then notice the 3 represents our polynomial of t. And so m is just 0 here because we don't see any t, so it's technically degree 0. And then r, because there's also no e here, it's technically e to the 0. R is 0. Okay, so our root associated with this non-homogeneous term matches with one of the roots from our auxiliary equation. It matches with one single root, it was 0. And so that is why we're going to pick case 2. So for case 2, we have this format of our answer, and S is 1 for case 2. Okay, so we fill in our values. S is 1, M is 0, R is 0, and we get Y2 equals A0 T. All right, we do this one more time for our third term over here. So we say our differential equation equals 7t e to the negative t. This non-homogeneous term has similar format to the last one, p sub m of t times e to the rt. And this time it is going to be a polynomial of degree 1, because notice the 7t, there's a t to the first power. So the degree on this polynomial is 1. And then our r value here is -1. Okay, now this root from our non-homogeneous term matches with one of the roots from our auxiliary equation, but it matches with the repeated root, the one that we had twice from our auxiliary equation. And so because that's repeated and it matches, that's why we're going to pick case 3. So case 3, we have this format for our answer, but S is 2 in case 3. Okay, so then we fill in our values. S is 2, M was 1, and then R was -1. And so Y3 equals A1 t cubed e to the negative t plus A0 t squared e to the negative t. Okay, so we had 3 separate solutions because we broke down what this equation equaled into 3 separate equations technically. And so we're just going to put them all together for our answer. But real quick, I'm going to go ahead and rename the coefficients just to kind of clean this up, because technically these are not the same A0 values and B0 values and all that, because it came from 3 different equations when we separated this. So I'm just renaming things. I just called A not A, B not is B. From the second equation, I'm calling that C. And the third equation, I'm calling these coefficients D and E. And then by our superposition principle, the solution to our third order differential equation that equaled this combination of these 3 non-homogeneous terms has a solution that's y1 plus y2 plus y3. So it equals y, which is all of the combination of our 3 answers here. Okay, so that's our method of undetermined coefficients revisited, and our introduction and use of our superposition principle. That's it. Take care.